Oh, hello everyone. From the last class onwards, we started discussing about Bayesian classifier for normally distributed classes. That's what we started. Before the class, before that class, in one or two classes before that, we were discussing about the Gaussian distribution as such. We started with the 1D Gaussian distribution, generalized expression for 2D Gaussian distribution, how those graphs, how those plots would look like in a 2D case, and what would be the shapes of the ISO curves for varying values of variance. These are the things that we have seen. And after that, we came to the Bayesian classifier for normally distributed classes. That's what we started in the previous class, where we are assuming the likelihood probabilities are having Gaussian distribution, right? And then if you recollect how a classification is done is you look at a posteriori probabilities. For a given feature vector, you will calculate the a posteriori probabilities for all possible classes and you choose that which has maximum value, right? Maximizing probability of x bar given omega into probability of omega I. Now, this probability of x bar given omega I is where you assume this likelihood function, you are assuming to have a Gaussian distribution. And with regard to the boundaries between two classes, right? That we would get it by figuring out where this a posteriori probabilities are equal, those two, correct? So that's where, for example, this function of Fij of x bar is defined, where this particular function you would be calculating for the ith class and jth class, both of them are equal. These a posteriori probabilities are equal at the boundaries. So if you take that, if you subtract Fi of x bar minus Fj of x bar, then you could say on the if this value is less than 0, that belongs to ith class. If it is greater than 0, that belongs to zth class. And if it is equal to 0, that belongs to, that is the boundary between the two classes, right? After that, we have taken one more step forward, where we don't really want to calculate all the time these a posteriori probabilities for various reasons. The complexity involved in that, the modeling of these curves, and many other things are there. So we want to apply on these Fi of x bar, Fj of x bar, or some other monotonically increasing function, which is easy to calculate, are having certain advantages in terms of the calculations or complexity. Okay, one such example, a simple example in the current case, is you simply take a logarithm of it so that this exponential function would come out of that and you will get a simple expression for that. Then we have noticed that as long as your function is monotonically increasing, what does that mean? If your f of x bar is increasing, g of x bar is also increasing. So f of x bar, when I say this, that value could be that corresponding to the ith class or the jth class. So one such function we have considered is natural logarithm. Then what can we say about these decision boundaries and to which class does that belong to? Same thing applies there. Gij of x bar equal to g of x bar minus gj of x bar. If this is 0, that would be your boundary. Less than 0 belongs to ith class, greater than 0 belongs to zth class, because this is a monotonically increasing function. What else did we do then? We have applied this logarithmic function on your fi of x bar. That's what we tried in the last class. And we also, to get some intuition about how does it look like, we have considered a two-class problem. That means, sorry, not a two-class problem, a feature vector with two components. So L equal to 2 we have considered, right? And then what else did we consider? This is a diagonal matrix. The variance matrix is a diagonal matrix with its diagonal values equal. That's also we have considered, so that we could get some idea about how does it look like. So then what we did, we just finished doing computing GI of X bar on this, which is simply taking a natural logarithm of this Fi of X bar, right? We did some simplification on that. Finally, we arrived at this expression. Uh, and then since we considered there are two classes, two components for your feature vector, our feature vector size is 2 cross 1. So x1, x2, and each feature vector components respective mean values are considered here. We substituted there and ended up this expression. So what can we see in that expression? The whole thing is multiplied with 1 over 2 times sigma I square into x1 square plus x2 square minus 2 times mu I1 x1 plus mu I2 x2 plus mu I1 square plus mu I2 square plus natural logarithm of probability of omega I minus 1 by 2 into natural logarithm of determinant of sigma I. Again, this is having such a nice pattern. It is not difficult even to remember this and then make an interpretation about that. Well, it is having quadratic terms. So if you, in general, you call this as quadrics, which means for varying values of x1 and x2, this can take the shape of an ellipsoid, shape of a parabola, hyperbola, or in some cases, any other possibility. All possibilities are wide open here, right? This is till this point we discussed in the previous few classes. So let me now take you through some examples of how the visualization of these things would look like, so that that will give us some idea. Right. So I copied the same expression here, what we got for the monotonically increasing function that we have applied on the on Fi of X bar, which is in a way representing your a posteriori probabilities. Okay. So then here are few graphs or plots for some of these. So we are right now considering L equal to 2. These are all plots for L equal to 2, because that's something you could draw and see clearly in a three-dimensional space. So this is what is considered here. Again, in addition, you should have comfortability and expertise and skill, both in terms of the math as well as interpreting these graphs and equations also. I keep repeating the same point. Don't think one as substitute for other. So let's try to get some interpretation for these graphs also here. So the first plot here, there are two mu1 equal to 0, 0, mu2 equal to 4, 0. What does that mean? So we consider two classes here. The class 1, the mean value of that class 1 is at 0, 0. That means you have two feature vectors, x1 here on this and x2 here. Okay. So first thing it is saying is, well, you have for the class 1, the mean value at z is at 0, 0. For class 2, it is at 4, 0. X1 equal to 4 and x2 equal to 0. You have mean value. Variances are diagonal matrices. That means among the components of the feature vector, they are in fact statistically independent. That's what this will tell us, right? So that's what, okay. So this is sigma 1 and sigma 2 are 0.3, 0.35. Okay, hope you also remember. Then these are what you get is kind of ellipses is what you get for each of them. If you recollect, when these are off diagonal elements are 0, what you get when particularly these values are different is you would be getting ellipses. Sigma 2 is having 1.2 and 1.85. So is variance more or less compared to sigma 1? Is the variance more here or less for class 2?
More, sir.
4, right? Now you look at this graph here, this plot here. At 0, 0 centered, along the x-axis, the variation is 0.3, and along y-axis 0.35, almost similar, but still it's an ellipse there. And uh, since this variance is less compared to this, obviously it's a PDF. Essentially, the Gaussian distribution is 1 over root 2 pi into sigma. The magnitude is scaled by that sigma value, or it is here more general determinant you will take, and that square root of your determinant is what is going to come in the denominator. The determinant is less, right, which is there in the denominator. Of course, the peak value will be relatively more when your sigma value is less. So obviously to this it's high. Look at the second one. The variance is, well, 1.2 here and 1.85 along x2. Of course, it is bit more spread in y-axis than in x-axis. But then again, this being in the denominator, your variance being high, the peak value, the whole thing is scaled down by a small value. So this comes down a bit here. Now, the color convention that is used here is that whenever for the class 1, the value is high, it is shown in red. Otherwise, it is shown in the gray color. You remember that you know the graphs, even 1D, you would have noted earlier that if you have a peak value of Gaussian like this and another with a larger variance, beyond this particular points, it will be more on both sides, right? And this base value for over a large region, unless you are going to minus infinity and to very far away from the centers, that will have more value for that curve or for that Gaussian, which has more variance. So that's why you would see even on this side of that, this will be all 0, and to a particular region here, this would be more, right? And then here is the ISO curve on your right hand side picture there. For omega 1 showing you the class 1, omega 2 showing you the class 2, and this is the ISO curve for that is a 0. Hope you are all following me. Gij of x bar, that is 0, we have been talking about, right? It is around the boundary. Gi of x will be equal to Gj of x. So we are after all plotting the contour associated with the points where both these functions are equal, because that is turning out to be the boundary. Is that fine? This is the another possibility where mu first class has 0, 0 mean. Second class has a mean of 3.20. Okay. And that means at 0, 0, you have the center of your whole distribution is centered at 0, x1 equal to 0 and x2 equal to 0. The next one is at x1 equal to 3.2 and x2 equal to 0. Then look at these covariance matrices. Again, these are statistically independent feature vectors. First one, along x1, it is 0.1, along x2, 0.75. So there is more variance in which direction, along x1 or along x2?
Along x2, sir.
Right, 0.75 is there along x2. So can you see that from this red colored distribution there, where you would see that, of course, now that being 0.1 being small here, this 0.75 being larger there, you see that orientation. Hope you are able to convince yourself and see why it is in that particular way. Now, see the covariance matrix for the class 2, here also the off-diagonal elements are 0 and the diagonal elements are interchanged. That means obviously it is whatever is there earlier in x1 will now become x2, and whatever is x2 earlier will become x1. That means x1 and x2 are fixed here. That means your whole distribution shape would be like as if rotated 90 degrees. So that you should be able to observe here, right? And now it is again mathematically anyway we have seen to an extent why we get parabolas, hyperbolas, ellipse and all these things. If L is greater than 2, ellipsoids and hyperplanes you will get there. But again here iso curves for 0 are plotted here, and that's what you would get. And what is that shape of iso curves for value of 0? Again, for those points, I'm still calling pixels, sorry for that. For those points where the value is more for class 1 are shown there in red color, not that distribution is not there in gray color, just to see it conveniently so that even the distribution you could observe there quite comfortably, right? Again, whenever the variance value is high, okay, so x and y now, since this is a nice simple trick that they have done to nicely demonstrate and create an example here where you could see the hyperbola. So this was the figure again from the textbook, same example from the textbook. I feel there is some small mistake is there in the isocurves graph. That's again I picked it from the textbook. Can anyone make a guess on what could be wrong with that value? I feel this should be omega 1 here, and this should be omega 2 here, and similarly, this should be omega 2. So, because around this, inside this hyperbola, it is this distribution that is more, and that is where you assign it to that particular class, and outside that it will go to omega 2. So that's what I feel a mistake there. Okay, you think about it, and if you think otherwise, and if you find a mistake in what I am inferring here, please do let me know in the next class, if not in this class.
Sir,
Yes,
over here, when we define this matrix, the covariance matrix sigma I, sir, uh, this should be sigma I1 square and sigma I2 square.
very good. Yes, that is possible. It's just that for the simplification, I considered both of them have same variances. To come to a conclusion here that you could see here, if this is same, this is more like an x1 square plus x2 square by I square. For interpretation and for simplification, I considered it. But again, when it comes to the examples, since I am plotting it numerically and not from this equation, the switching has been made to cases where I could have different variances in x1 and x2 direction. That's a good point, which I haven't explicitly mentioned. This is the case where I considered the variances in the for all the components of the feature vectors for a given class are same. So it is just dependent on a class. For a given class I, it is sigma I square is the variance. Okay, but when it come to examples, I took a deviation here, just following the textbook. In similar lines, I followed the textbook, where we allowed here to even these two to have different variances.
Sir, then how will this formula change, sir, for GI of X?
Yeah,
What
see,
will get added?
right. All that would happen here is, if you notice here, I am taking this sigma square is common for all these things. See here, the sigma I, okay, I am writing it as 1 over 2 sigma square here. Now you could work out here, if you have sigma I1 square, sigma I2 square, when you take the inverse, basically this isn't there an inverse here? That's
Sir,
what
we
we
had
discussed
written
in the
we had written
previous.
it as an identity,
Correct,
and
correct,
that is how we got the identity matrix and this
correct,
sigma I square value. So if it is sigma
right,
I1 and sigma I2, then we cannot take it as this identity. It will remain.
correct, correct. So everywhere you need to write it in terms of the matrix there.
That's the only
That's
difference,
what
right?
you need to write it. You cannot simply write it as sigma square. That you could notice that it will still come out everywhere, except that there is a matrix outside.
Understood. So that's all I was asking.
Yes, very good, very good. Hope the others are also are fine with the kind of are clear with what we are doing and what has been shown in examples. There is a variation there. And I'm sure, given that I have done this derivation, now if I ask you that, as one of you has pointed out, sigma I1 square and sigma I2 square, even if I give you, I'm sure you will be now able to derive the expression. See, even let's say you could see if I am getting an ellipse with both same, if it is different, this is both same is in fact a special case of both being different. Okay, if I put instead sigma I1 square here, sigma I2 square here, right? Then what would happen? There a special case of that would again be sigma I1 equal to sigma I2. For a special case itself, I figured out here it can take the forms of ellipsoids, hyperbolas, parabolas. So obviously, a general case is this being part of a general case. There also you could expect all different types of shapes. Hope you all agree with that. The inferences that we have drawn, despite taking these two variances to be equal, this is very much valid. These all these various shapes are still possible even when you consider here sigma I1 square and sigma I2 square, because this case both being equal is just a special case of this. So if you get different shapes here, all those shapes obviously you will be getting as a part of this thing also. Okay, further rotations and all other things also would be happening here when you are taking that. Now, we will continue and see our discussion. Now, we will see how the decision hyperplanes would look like geometrically as well as mathematically. Again, to make this mathematical problem tractable and for us to make some inferences, I would make few more assumptions also about the kind of distributions I'm going to have. So my objective here is to work out and figure out the decision hyperplanes. I'll continue that. So let me further assume that uh, the covariance matrices are same for all classes. The covariance matrices are same for all classes. That means I already made an assumption that diagonal elements are same. Further, I am assuming that all of them are having the same covariance matrix, all classes. So that means what I am assuming here is sigma I is equal to sigma. I could write it as, because it is now independent of whatever class I have it. Okay, so this is a very special case we are going to discuss. This is a kind of a very special case here, because this might not happen to in all situations. So this is a pretty special case. Can you make any guess on what could this result in? What kind of decision planes would I get with this? Can any of you make a guess here? So this was actually the question I was asking you at the end of the last class also. What could be the scenario if sigma I square is same for gi of x bar and gj of x bar? Then your decision hyperplane you will get when gi of x bar equal to gj of x bar. And from that equation, once you solve that equation, you will get the x bar value. You call it, let's say, x naught bar. That tells you at which point these two classes have a boundary, right? Or plane. It need not be a point, it's a plane. So can you make a guess on what could be the shape of that?
Then we can remove these terms from that equation, sir.
Which terms can you remove?
Minus half natural log of sigma
Very
I.
good. That's a
And
good first step to begin with. Excellent. I could remove this, my GI of, because both sides it gets cancelled about. What more gets removed when I do that? Is that the only term?
x1 square plus x2 square.
That's right. That's right. This is so obvious. I thought you would tell it much ahead. x1 square and x2 square are getting cancelled out. And now if you bring all those terms here, what would be the impact of that in terms of where you get now x1, x2? See, finally, what is it that you are going to solve when you are saying gi of x bar equal to gj of x bar? What is it that you will solve then? For what? Is it mu? Is it x? Is it p omega? Is it sigma I? Which is the variable that you are going to compute from that? When you make gi of x bar equal to gj of x bar to find out the decision plane.
x1, x2.
Correct. Now, can you tell me the result, the locus of all points of x1 and x2 when gi of x bar equal to gj of x bar? Do you think still you could get some ellipsoids, parabolas, and all those stuff?
Only straight lines.
Right. Correct. So had it been a single feature vector with a single component, this would have been a straight line. Now you have, yeah, this you could think of it as a plane now, because x1 and x2 are there, right? If it is x1, if it is a single vector, that's a line. Yeah, if there are x1 and x2, the separation decision plane will be in fact a simple plane there. But it cannot have any quadratics here, because the quadratic terms contributing there are same, irrespective of whether you are computing gi of x bar or gj of x bar. They are same, and thus gets cancelled out on both sides. And what you would be getting there is a simple plane. Or if you still come down to one-dimensional feature vector, as you rightly said, this would be a line. Is everyone able to see this interpretation from this equation? I'll of course do it now mathematically, but that in fact doesn't require any mathematical treatment. Just by contemplating on this equation without writing any further simplifications or modifications to it, you should be able to get this. So let me come back again now and let me finish my mathematical treatment of this and go ahead. That was the earlier equation that I had. So gi of x bar, that I just copied from the earlier ones, the equation that you see there. Now let me write gi of x bar is equal to minus 1 by 2 into yeah. So in the denominator, what do I get there? Sigma square, right? And now let's take this transpose there. How did we write that? X bar whole transpose minus mu I bar whole transpose. This multiplied with x bar minus mu I bar. Correct? So this is what I have here for the first expression in the GI. I'm just simplifying the equation that you see here. Okay, that I am writing here first. Then natural logarithm of probability of omega I. In the previous class itself, I have dropped minus L by 2 into natural logarithm of 2 pi, because after all, even if you even after removing or keeping it without that, irrespective of that, it's a monotonically increasing function. Okay, minus 1 by 2 into natural logarithm of determinant of epsilon. So I am now dropping this term also now, because it's same for both. So gij of x bar, which is gi of x bar minus gj of x bar, this will not be there. Now let me do simplification for the rest of the terms here, which is x bar transpose times x bar and minus x bar transpose times mu I bar minus mu I bar transpose time x bar. I have written very similar things in the last class also. Mu I bar transpose times mu I bar, right? Plus natural logarithm of probability of omega I. Now I could redefine my GI of X bar. I defined by dropping there -1/2 into natural logarithm of sigma. Now, what else can I, which term among all these terms I have written, I can further drop, further ignore while I write GI of X bar, but still get the same results. What is that term here? See, finally keep in mind your J of X bar equal to GI of X bar minus GJ of X bar. If this is greater than 0, it belongs to ith class, less than 0, jth class, equal to 0, boundary, right? I am dealing in terms of these discriminant functions. My J of X bar is the discriminant function, right? Now, what is the other term that I could comfortably drop in GI of X bar, still getting the same result?
X transpose X.
That's all, correct? This is all I discussed already here when I am saying the quadratic term wouldn't be there. That's the only quadratic term which would, it has nothing to do with I of X bar. Look at all the remaining 4 terms there. They all have something specific to ith class or jth class. This is the term which, for example, if you consider x1 and x2 as your feature vector, you will get x1 square plus x2 square. Okay, so I am dropping this term also here. So now I'm redefining my GI of X bar again. So I'm keep redefining my GI of X bar by just keeping those terms which are required for me. Okay. So what am I left with here? Well, as so I could do 1 over 2 sigma square into this. By the way, I forgot to keep here -1/2 sigma square minus, so here also -1/2 sigma square. Do you remember by any chance, how could you simplify that? X bar transpose multiplied with mu I bar and mu I bar transpose multiplied with X bar, how are they related?
They're same.
Right, they are same. If you take x1, x2 for X bar and mu I as mu I1x and mu I11, mu I2, it is nothing but both the terms are x1 multiplied with mu I1 plus x2 multiplied with mu I2. You could simply verify that. This is of course true for any length of vector. It not is necessarily just 2 classes. Okay, that now that is that minus of minus I'll take out. So I'll get plus 1/2 sigma square into mu I bar transpose into X bar. I'm writing that. Okay. Then I would write -2 over 1 over 2 sigma square into mu I transpose into mu I bar plus natural logarithm of probability of omega I. Okay, so this is my new GI of X bar that I am going to define. Okay, now you could see
Sir,
here. Yes, sir. Yes.
sir, 1, 2 is extra in the first one.
Yeah, good point. Sorry for that. Good. Thanks for pointing it out. Very good. So I'll simply write here 1 over sigma square. Correct? Now it is fine. Good.
Sir, it is fine. There's a question, sir.
Yes,
Sir,
please.
why could we not remove this X bar transpose X bar in the previous expression which we had got for GI of X bar? There also it was the
Very
same.
good question. Very good question. Can anybody try answering this question? I thought somebody would ask this question. I'm glad you asked it. Why did we not remove this expression earlier? Why are we only deleting this expression now? What is the additional thing that
Is it
that
because sigma I is not equal to sigma j, sir?
very good. That's the answer.
Okay,
Earlier,
now
you
I've understood.
have x square by sigma I square and x square by sigma j square there you have. Both, see, finally all we need to keep in mind is this expression. Gij of X bar is Gi of X bar minus Gj of X bar. So what would happen is on one side you will be getting 1 over sigma I square, and on the other side you will be getting 1 over sigma j square. Now I am writing this gi of x bar as wi times x bar minus or plus, let me keep it, w times I0. I'm keeping it. Notice here, this term has nothing to do with x bar. So with respect to x bar, for varying x bar values, for a given class I, this is constant. Of course, if I go to class J, the probability of omega j could be different. For that class, the mean values could be different. So mu j transpose times mu j is different. So this is a constant. This is a constant value for a given class, which I have written as wi0. Just to say that this is a constant, I kept there wi0. And your x bar is getting multiplied with mu I transpose over sigma square, right? So this is what I have written as W, maybe let me write it as Wi transpose here. It has its own advantages there, because I could simply take mu I over sigma square as my Wi there, right? So I am writing it as this function gi of x bar. So this is all I already explained without writing a single equation there. Gi of x bar is like ax plus b form. Do you see that now? You are applying a transformation on x bar through wi transpose. Why did I keep wi there? Because that's varying with respect to I. So I made it as wi transpose times x bar. For another class, this would be different. So I made it as wi transpose x bar. So that what is the conclusion I could draw here? My discriminant function, is linear. Why is it so? Just now look at gij of x bar is equal to wi transpose minus wj transpose times x bar, right? Plus wi0 minus wi1. This is my discriminant function. Of course, if you can look at it as gi of x bar also, either you look at there or gi of x bar, you now see that this discriminant function is linear. Okay, so maybe in the interest of time, I have to stop here. Before that, I'll just show you one graph to convince you this. This is how you will see that now. So this is the graphs that you are getting. Of course, I am not keeping here the exact values of the variances, but again, you could see that if you consider this as your x1 axis, you have high variance along x1 axis, and this you have a smaller variance here, x2 axis, but your variances are same for both the classes that you could see from so it is just the same distribution displaced. When you do it even graphically also, you could visualize that you have a function, a decision plane, which is linear. Okay. So one quick observation that you could do here is look, even with the simple Gaussian functions, by playing with variances, you should, by this time, you would have realized that the kind of classification boundaries that you would be getting, that you need to find out, these are the boundaries that would separate each class. Essentially, what should a classifier do? It should be able to separate. One way of solving it is you find out the decision planes. You could see here, even for a simple Gaussian distribution, you could have boundaries that are ellipses, or ellipsoids or hyperplanes there, which are associated or corresponding to these ellipses you could get, or you could get these hyperbolas and also linear decision planes. And when do you get these linear decision planes? If you are just running a neural network, you will never realize when you get these things. At least some special cases you could see here that is telling you that if you have same variances for class, the kind of boundary linear decision plane is good enough to separate two classes. If they have different variances, you might end up with very different kinds of decision planes. Okay, I'll stop here in the interest of time. See you in the next class. Bye. Take care.